Hello everyone, welcome back to ptet.chemistry channel. So my name is Dr. An, and in this tutorial video, I'll go through this restructured format for my 9701. This is A-Level Cambridge International for the November 20 paper 1-1. So for those of you who have seen my community post, you have understood that why to resort to this restructured format without showing the question paper due to copyright issues, which I'll not dwell on further. So this is the second full paper 1 for the A-level paper, which I've done in this format, and people seem to be alright with how the previous one went, so I thought I'll try again with a different paper. So without further ado, let me just jump straight into the first question. Actually, I forgot to mention something, which is a bit of shameless self-promotion. So don't forget to click the button on the bottom right if you haven't subscribed to the channel. To do that is entirely free and it will support the work. And do share the channel with all your friends, chat group, juniors, seniors, teachers, relative, whoever else you think the channel might be useful for. And you can find me at ptet.chemistry, that is ptet.chemistry on Facebook, Instagram and Twitter to get connected and send in your best wishes or your messages or your questions, which I'll try my best to answer, but you know, my time is pretty limited these days. Anyway, on to the first question. So they're asking for which statement is correct. So the idea is when you are doing multiple choice, it's very important that you circle or underline or whatever on this kind of information so that you know you are reminded of what you have read the first time. When you read through the information, you are not you are less likely to be tricked rather than having to waste time and do it all over from the very beginning again, especially when checking your answer. Now, as for option A, it's saying that it's the isotopic mass. So the isotopic mass is supposed to be a whole number, and the value that they're given you is 35.5 is entirely wrong because that is relative atomic mass. That is to do with the average value, blah, 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 blah. It's to do with the definition which candidates should be able to define. There were 4 definitions in the syllabus under relative masses, first of which is relative isotopic mass, which is the only one out of the 4 which is not to do with average. And you got relative atomic mass, you got relative molecular mass and relative formula mass, which are all to do with average value. So as you know, chlorine exists as 2 isotopes, chlorine 35 and chlorine 37. I should put them together under isotopes. And then together you will see in the periodic table they give you as 17 and 35.5. That is labeled as relative atomic mass in the periodic table, which they never lie to you, and you have the periodic table in front of you which you can use. Now they're saying that relative molecular mass. So relative molecular mass is a shorthand form is just MR. MR of CO2, we just get it from the sum of the relative atomic masses, so 35.5 times 2, which is 71, so it's not 70, so B again is wrong. The next one, C, they say ICL. ICL is just basically a diatomic molecule of 2 halogen atoms, so it's just going to look the exact same thing just like the halogens, with a single covalent bond between each of these groups 17 elements, which have 7 valence electrons, so they will share 1 valence electrons to complete the outer shell. Get it from the data booklet, so 126.9 plus 35.5, they give me 162.4 on the calculator, which is exactly the MR as expected, so C is actually the correct answer. Just very quickly, let me just show you why D cannot be the correct answer. They mentioned something about NaCl. We know that NaCl exists as a giant ionic structure, even from your year 9 O-level or IGCSE syllabus. So we use this term called relative formula mass, which is one of the 4 definitions as I mentioned, as stated in the A-level syllabus. We use this to represent for 1 formula unit, and they use the term molecular there. So the molecular is definitely wrong because, well, wrong in the context of technicality, but in the context of calculating the relative formula mass, we still use this expression called MR of NaCl, which you can get from the data booklet 23.0 plus 35.5. Pardon me, I might be wrong with this. Oh no, it's correct, 58.5. So it is wrong not because of the value, it is wrong because of this thing called molecular. Question 2. So this is about calculations. So we have strontium oxide plus aluminium giving you 3 strontium plus this weird looking Sr3 Al2O6. If we think about it, well, this question is not about redox, but it is actually a redox reactions. Strontium is in group 2 metal plus 2 oxidation state because the oxygen is -2. The aluminium there is existing as the metal itself, so it's 0 oxidation state. Strontium is 0 oxidation state because that's the element itself. This is a bit tricky here. So if you think about this, if each aluminium is +3 and each oxygen is -2, then what you're going to get is 3 strontium plus 2 times +3 plus 6 times -2 is equal to 0. So 3 strontium equal to +12 minus 6. 3 strontium equal to +6. Strontium is still +2. So you know, this is actually, this strontium going to this strontium is not a redox, but this strontium going to this strontium is a redox. So this is your reduction because this is a decrease in oxidation number. And of course, that thing there going to the aluminum 3, that is your oxidation there. Jumping straight to the question. So, well, there's something I should have done from the very beginning. I should have jumped straight onto the question. Let me just cut that and put it onto a new page because we'll do a calculation question. So some viewers have actually, you know, like previously commented that, you know, I should just jump straight to the questions, but it is my channel. I get to do what I want. My goal here is not just to get to the answer, but to show students who are probably using a lot of past papers for revision that it's very important to actually cover theory before you just jump straight into past your paper question. Now we want the maximum mass of strontium metal. So we want strontium metal, which is this one, and we want from the reduction of the strontium oxide. So we have that thing. If you watch my previous tutorials on mole calculations, you will know that I love to set up my expression like this, where I write down the mole of that substance, mole of strontium over the mole of strontium oxide. I never write down the number in front because the number in front is just a stoichiometric ratio. It's just to do with mole ratio. It's got nothing to do with the substance itself, which we don't put a number in front at all. From the balance equation, you have 3 mole of strontium. So on the top, I have got strontium. So on the top, I put down 3 mole of strontium from 6 mole of strontium oxide, from 6 mole of strontium oxide. This is from the balance equation. Some of you will have been wondering, does it matter if it's the other way around? It does not matter whatsoever in this method because all I did was I just label it. I just label the 2 things I have, whether they are this way around or the other way around. I will follow everything based on what I have written. So basically it's based on your answer, based on what you write, rather than, you know, following a fixed, a particular format or prescribed format. On the other side is basically the actual amount, and we're dealing with masses, so we'll be using mass over MR. If I think about my MR of strontium oxide, there will be 87.6 plus 16.0 from your data booklet. They give me 103.6. And of course, I don't call it MR, I call it relative atomic mass of strontium. Straight from data booklet is 87.6. Now on the top here, I have strontium. So I'll have the mass of strontium, which is 100 gram, divided by the AR, because this on top there is about strontium. So I just use strontium, mass of strontium over the relative atomic mass of strontium. And actually I was wrong. I am very wrong because the top bit, it is strontium, but I want the mass of strontium, I beg your pardon. I want the mass of strontium, so divided by 87.6, this is my unknown. At the bottom, I will have 100 gram of the strontium oxide divided by 103.6, which is the relative molecular mass, well, should I say formula mass for the strontium oxide, which has a giant ionic structure. Now all I have to do is rearrange my equation and I get the mass of strontium over 87.6. If I just move this up there, it's a cross multiply kind of exercise. So that is equal to that. For those of you with keen eyes for numbers or mathematics, you could have done this straight away by moving up 87.6 to the very top, and that will be equal to that. But for the sake of different kind of learners with different speed of dealing with numbers, I'll just do it everything step by step. And hopefully now, after you rearrange it to get the mass of strontium, you press it to your calculator and you will get 42.278. And this thing has no meaning unless you put a unit to it, because we have done mass over mR, the mass is in gram, just like this mass was in gram there. Of course, the answer given is not going to be like that. One of the answer given is to this thing, is to 3 significant figure. Based on the data given, the accuracy was 3 significant figure. So, you know, that's option B there. So jumping straight into question 3. So what do we have here? We have a single, oh, this looks strange. What is this? 32 sulfur plus something, and then plus X, they call it plus X, and then they give me 32 phosphorus. I should really put in my proton or my atomic number. So proton number of sulfur is 16, this is 15. So this is the only product, hang on, in the process a proton is emitted. A proton is emitted. Emitted mean given out. Emitted mean given out. So it is a product. I get a proton. So meaning to say a proton is one atomic number because it's one proton. They say a proton, meaning one. And proton is also a nucleon because proton is inside the nucleus. So I'll have one nucleon. So I have one nucleon because I have one proton. So I give you that phosphorus, one of these, and one protons. So at the bottom, 15 plus 1 give me 16. So this means this must be 0. And then I've got 32 plus 1, which is 33. But I only have 32, so this must be 1. Because the nucleon plus the nucleon give me the sum of the nucleons. The proton number or the atomic number add up to give me 15 plus 1, which is 16 there. So this is X. It has got no protons, but it has one nucleon. So your job is really, what is nucleon? Nucleon refer to proton and neutrons, but I have no protons. So therefore 10X is equal to a neutron, and that is your option C there. On to your question 4. So in which of the following, when in liquid form, only intermolecular forces based on temporary dipoles? So you got temporary dipoles, have I spelled that correctly? Temporary dipoles are sometimes called induced dipoles. And induced dipoles are basically what you have learned as van der Waals forces in your Cambridge International or any other 16 to 18 years old curriculum. So they want only induced dipole, that means they want only van der Waals forces. If we look at the options, so you have got bromine, which exists as Br2 diatomic molecule, and then you got ethanol, CH3CH2OH, you got hydrogen chloride, which is a simple molecule like this, which can dissolve in water to give you hydrochloric acid. So do not be confused about what is hydrogen chloride as a molecule and also hydrochloric acid as an aqueous form of HCl. There's a mixture. Now in terms of what I'm going to do, I usually like to think about this kind of thing in terms of what do they have. Van der Waals, bromine will have van der Waals. All of them have electrons, all of them have van der Waals. If I think about my permanent dipoles, so permanent dipoles refer to, is it a polar molecule, not just polar bond, is it a polar molecule or is it a non-polar molecule? And last but not least is hydrogen bond. There's no hydrogen here to begin with, so there's no hydrogen bond there. And this has no permanent dipole because it's non-polar. How do I know it's non-polar? Because, well, you know, this atom and this atom are exactly the same. That means they both have equal electronegativity, and therefore there's no difference in electronegativity, which means we already got the answer just by looking at option A. That is where you only have van der Waals forces between the molecules. Just for completion's sake, we can see that ethanol is a liquid at room temperature and pressure as a result of a reasonably high melting and boiling point, well, high boiling point essentially, because it's got a lone pair, well, it's got a hydrogen bonded to of oxygen, which is one of the three highest or most electronegative element. So hydrogen bonded to F or N is the first condition, and the electronegative element must have lone pairs that can form hydrogen bond with a neighboring molecule. That's why hydrogen bond is an intermolecular force. Hydrogen bond is basically a much stronger version of permanent dipole. If you have hydrogen bond, you definitely have permanent dipole. So HCl does not have hydrogen bond, but it is polar due to the different electronegativity between the two atoms. Water has hydrogen bond and is also a polar molecule just like that. Question 5 is about copper. So they're asking you on the structure of copper actually, because high melting point, anything to do with melting point and boiling point is to do with structure and bonding. So copper has a giant metallic structure. As you know, in your head, you can probably imagine that the giant metallic structure consists of the metal cations suspended in a sea of delocalized valence electrons. What a lot of students don't know is that these are just the valence electrons and not the total number of electrons. That will be the van der Waals forces kind of factor. So these are sea of delocalized. So the electrons are no longer in the fixed orbital. In fact, they are delocalized and they are free to move. And that is why metal can conduct electricity even in the solid state, because these electrons are not localized at all. So the structure is giant metallic structure, and to melt or to boil, so this is essentially just like preparing for structured paper. To melt or to boil metal, we need to break strong metallic bond. So these are all part of the inorganic chemistry component of A-level chemistry, where you need to be prepared for the 4 different scenarios of the structure as stated in the states of matter topic or the syllabus or the specification by the Cambridge International. So this is about wordy kind of questions. So we know that it's between the metal cations, which are positively charged, as well as the electrons, which are negatively charged. But it's not just any electrons. It's to do with the delocalized electrons. So you need to be careful that you're choosing between the cations, the copper ions, which would be the metal ions, cations, and the delocalized electrons. That give you option B there. Question 6, so what we have here is, they're asking for which one is numerically equal. So they're using like fancy word, but what could be interpreted by this is that they will have the same value. All right, they will have the same value, they will have the same magnitude, you could say that, the same magnitude. All right, so they are basically identical reactions. So if you look at option A, you have atomization of CH4. Atomization of CH4 means from the molecule which has 4 carbon-hydrogen bonds, you become 1 carbon gaseous atom and 4 hydrogen gaseous atom. Now formation of CH4 on the other hand is forming 1 mole of the substance from its element. So carbon plus hydrogen gas, and I need forming 1 mole, so I need 2 mole of the H2, and don't forget the stat symbol for the carbon. So as you could see, these and these are not the same. I want to say not the same. If they are not the same, then how can they represent the same reaction and have the same value? So that's how I know A cannot be the answer. If I look at B, what I have is combustion of CH3OH, combustion. So they will give me 1 carbon, which is CO2, and they give me H2O, and there's 2 hydrogen, so it's just 2 H2O, just like that. And I've got 2 oxygen and 2 oxygen, so 4 oxygen minus 1 oxygen. I need 3 oxygen atoms, so it's 3 over 2, like that. Don't forget, stat symbols are very, very important in this kind of topic. And they say combustion of graphite plus the combustion of 2 hydrogen. So if I think about combustion of graphite plus 2H2 gas, is that numerically equal? Well, that thing will give you the combustion. So this is combustion of graphite plus the 2 times the combustion of H2. And this is whatever they say, this is combustion of CH3OH. But as you could see, these and these are not the same. So there is something there. There is something there which has a value. So this is not equal to this, and that is why I can say B is also wrong. I think I'm kind of running out of space. So what I'll do is I will just put all of these onto the next page. Should probably start one question on one page to avoid this kind of problem in the future. So at least that will be much better. So in option C, I have combustion of graphite. Combustion of graphite is burning 1 mole of a substance in excess oxygen to give you the combustion products under standard states, under standard conditions as well. So there's a balance equation. So that is your combustion of your graphite. And then if you think about formation of CO2, I am forming 1 mole of the substance from its elements. The elements includes carbon element as well as oxygen as an element. And in their standard states, under standard conditions, you can tell that these two equations are the same. They are exactly identical. So just now, we were writing this for the formation of CO2. That's how you can tell the combustion of carbon is the same as the formation of CO2. There's actually another one where they are identical. So I'll just show on the side note that you should be aware that there's another identity, which is basically the combustion of hydrogen. When you combust hydrogen, you will get H2O as the product, but you're combusting 1 mole of these, so give you 2 hydrogen atoms, and there's only 1 oxygen atom here, so I must balance this with a half. So just now I said this was the combustion of H2, but if you look back and you can also see that, don't want to write another one, that this is also the same as the formation of H2O because you're forming 1 mole of the substance from its elements in their standard states under standard condition. So this is equal to the formation of H2O. Just like what we said in the previous question, the combustion of carbon is the same as the formation of CO2. These two are very, very important identity, especially in the theory paper. So we know C is definitely the correct answer already, which means D is not the correct answer. But I'll just very quickly highlight to you why D is actually incorrect. The neutralization reaction is basically H plus OH minus, give you H2O. So you have an associated enthalpy of neutralization with it, and you know that it will be exothermic because the recombination of the ions of opposite charges just to recreate the covalent bond without breaking any bond at all is always going to be exothermic. As you have learned in IGCSE or O-level, bond making is exothermic. Now if you want to form H2O, well, we have our equation up there. You will see that these are from its elements, these are from its ions, so these and these are not the same, and therefore they cannot carry the exact same value at all. So in the next question 7, so what we have is an energy cycle. So it's given to us that we have bromine liquid plus 3F2 gas going to 2BrF3 liquid. So obviously it's a lot easier with a question paper in front of me, but you know, we try to make do with what we have and try to make full use and kind of blessings on what we still afford to do here, which is just to go through the tutorials without going through the paper. Okay, so yeah, I mean there's the cycle given there. So what we have is we have the enthalpy of formation. This is the data given. We just need to process the data. The formation of the liquid bromine trifluoride is minus 301 kilojoule per mole. So let's try and find that. We are trying to form it from its elements in their standard states. So this thing is 2 times the formation of BrF3 because we are forming 2 mole of it. This thing is defined as the enthalpy change when you form 1 mole of the substance. You are forming 2 mole of the substance from its elements in its standard state. So this is going to be minus 301 multiplied by 2. Okay. How about the other one? The enthalpy change of the liquid to the gas. So we're going from BrF3 liquid to the BrF3 gas. So obviously this is boiling. So these are simple covalent molecules or simple molecular structure. Incidentally speaking, I'm not sure if you know this, but these are what you call a T shape. So they are like two lone pair and 3 bond pair. This is an interhalogen compound because it's between different halogens. So this is what you call T shape. And this thing is 90 degree to each other. And that is the 90 degree. And there's no bond angle between lone pair, bond pair, and bond pair because the lone pair is not a real atom. It's just a naked pair of electrons. Jumping straight back to the question. So this is boiling. As you know, boiling requires breaking the weak intermolecular forces between the molecules because it has a simple molecular structure. So we know that it's going to be endothermic because we need energy to break that weak intermolecular forces, and we are told that that thing is endothermic, which is plus 44 kilojoule per mole. So the liquid going to the gas, that is for 1 mole of BRF3 per mole. This is per mole of BRF3. So what we have here is we are boiling off 2 moles of BRF3, so we have to do 2 times plus 44. So this kind of stoichiometry or the multiples to which we must multiply them really depends on if you understand definition or not. That's the very reason why in the syllabus they always say candidates should be able to define whatever. They might not explicitly ask you to state the definition, but the definition is something that you have to be able to apply based on what you're able to understand from it. What are the change? So this other change is given. So this one is given by the question. What else? So this thing is what they want you to find, and they say what's the average bond energy of the BRF bond. Importantly, hope you can see that this is gas. Well, didn't write properly, but on the diagram it will show gas, and gas. So we can relate that to bond energy. Remember that in BRF3 you have got 3 covalent bonds. In 2 molecule of this, you will have 6 covalent bonds. You will have 6 times the energy of BRF bond. You are breaking all the covalent bonds into the gaseous atoms. Everything in the gaseous state is to do with bond energy, and you're breaking 6 of them. So you can see that in our cycle, so if I have these going this way, it's going to be equal to that going that way. So Hess law says that the enthalpy change of a reaction does not depend on which path you take. So I can take this path, for example. So there'll be 2 times minus 301 for the one at the very bottom. And I can add that and add that together. So plus 2 times plus 44 plus 6 times the energy of BRF, close that bracket and close another big bracket. Suppose what I can do is I can move the 6 down there, but I use a big bracket just to show that I'm moving this number to the other side. So be very careful when you are doing mathematics, when you're doing calculations. So I'm trying to be as careful as I can here. Not too sure if you can see what I've done. I move this number to the other side, maintain it, I put a minus because there's a plus in front. I maintain this thing on the other side, I put a minus on the other side. Use a big square bracket, divide the whole thing by 6, and press that into your calculator. And I hope you get this thing where EBRF, the top bit come up to plus 1212 divided by 6, and that gave me plus 202 kilojoule per mole, and that is option B as the answer there. Moving on to the next question. So question 8, they want the greatest change. Be very careful. They don't want the highest or the greatest oxidation number. They want the change in the oxidation number of the sulfur. Okay, so if we go through option A, so we have sulfur plus O2 giving you SO2. I don't care too much about the stat symbol because oxidation state does not depend on the stat symbol. This is the element itself, so it's sulfur in 0 oxidation state. I can work with the oxygen, but it's not essential since they are only asking us on the oxidation state of the sulfur. This is sulfur dioxide. Each of the oxygen is -2 in the compound. So what happened is you have 1 sulfur and you have 2 oxygen, each of which is a -2 in this compound. The compound itself has 0 oxidation state, that's why it's called a compound. There's sulfur plus 4 there. So the change the change there is from 0 to +4. So I can say the change is +4. If I go on to the next one, let me go back to blue, SO2. So these are all the changes that happen in the contact process in order to make H2SO4 in the industry. So let me shift that to that. That's sulfur +4, which we just worked out. You can do the same thing as what we did earlier to work out the oxidation state of sulfur and SO2. You can do the same thing for SO3 and you get sulfur +6. So the change there is going to be +6 minus 0 is +6. So I leave you to do that as an exercise on your own. SO3 plus H2SO4 giving you H2S2O7. So this is what you call oleum, something you have done in O-level or IGCSE chemistry anyway. It's part of contact process, reversible changes. So what we have here is we have hydrogen +1 in a compound and oxygen -2. Oxidation state, the rule of oxidation state for these atoms in compounds generally. I have 2 of the hydrogen, so 2 times +1. I have 2 sulfur. I have 7 oxygen. Altogether give me a compound which has no charge. So now moving everything on the numbers to the other side, I'll get +14 minus 2. 2 sulfur is +6. Sulfur is, am I correct? No. +14 minus 2 is +12, and I get +6. So sulfur +6 here is no change. So this is not a redox. Not a redox at all because there's no change in oxidation state. So it's going to be 0. There's not going to be any change at all. And of course, when you go to H2S2O7 plus H2O going to H2SO4, there are 2 of them. You should notice sulfur +6 from the previous example that we did. Last but not least, you can work out H2SO4. So +1 times 2 because 2 hydrogen, sulfur, and then 4 times -2 equal to 0. Sulfur you work out as +6, something you would have known as part of group 17 chemistry when we use corn sulfuric acid to react with chloride, bromide, and iodide. We work a lot with the oxidation state of sulfur in sulfuric acid as sulfur +6. So hopefully you should be able to get that without without having to work it out because it's part of your case study already. So these 2 have no changes in oxidation number. So from here it is +4, and the change here I've gotten it wrong again. I don't know why I keep on making this mistake. +4 to +6, that means +6 minus +4 is going to be +2. So this is going to be a smaller change than this one, which means the correct answer must be A and not B. Alright, if I make that mistake being 0, I've gotten this as the answer, but obviously the answer is A because I had a moment where I didn't read that it was +4. So be very careful what you're reading. You don't want to make this kind of mistake in the real thing. Question 9. So what we have in question 9, well, this is about oxidation and reduction again. So I'll just very quickly write down the equation, and then we can think about the oxidation number. So oxygen in a compound is going to be -2. Oxygen in a compound is -2. So let me see what other color I can use. Let's use green. Titanium there is going to be +4. We don't care about the number in front. So +4 -2 -2. The overall compound has 0 oxidation state. This is titanium +4 because you can imagine that the chlorine is chlorine -1. The chlorine there is chlorine 0 because this is an element chlorine. It's chlorine bonded to titanium, has -1 oxidation state. The carbon there is carbon 0 because this is carbon element. And the carbon there, the carbon in CO is going to be carbon +2. The carbon in CO2 is going to be, hang on, my line doesn't look very straight at all. Doesn't matter. So this is going to be carbon +4 because you've got 2 of the oxygen, each of which is -2. I think that pretty much sums up all the oxidation number of each of the respective atom. So which one is being reduced? They're asking for reduce. Which one is being reduced? We are looking for decrease in oxidation number. And that is what we have done in this exercise in terms of oxidation number. The other thing you can be thinking about is reduction is gaining of electron. As part of the acronym called oil-rich, oxidation is loss of electrons, reduction is gain of electrons. When you gain electrons, your oxidation number will decrease, so these two are linked with each other. Titanium plus 4 to titanium plus 4, you can cross out titanium because titanium has no change in oxidation number. Oxygen minus 2, no change in oxidation number. 0, chlorine 0 to chlorine minus 1, so hopefully you can see that there is a decrease, so that is your reduction. So our answer really is just B, chlorine get reduced from chlorine 0 in Cl2 to chlorine minus 1 in TiCl4. In question 10, so they have given you two equations. So they look like two, well, one of them is not equilibrium. The first one is not an equilibrium, so it fully dissociate, full dissociation. So there's no reversible reaction. But the second one is to do with the second dissociation, so that's going to go to SO4 2 minus, plus another H plus when you fully dissociate it. Now this is in equilibrium, and because you're in equilibrium, you can talk about equilibrium constant since the reaction didn't go to completion. Alright, so if I look at equation 1, what can I expect out of it? You want Kc. If we think about what Kc is for this second expression, which I should really write as equilibrium, as given the question, it's going to be concentration of SO4 2 minus times the concentration of H plus divided by the concentration of HSO4 minus. Now, these H plus come from these, but before you get these, you also have the H plus from the first reaction. So the H plus from the reaction 1, which fully dissociate, is going to be so much more than the H plus from reaction 2, because this is a strong acid, is full dissociation, whereas this is only partial dissociation. So you already have these in the same solution mixture as these come from these, and these further dissociate into these. You don't have a lot of these because they are in equilibrium. So this is related to the concept of acidity in A2 ionic equilibria. I'm pretty sure that you will do this eventually. So there's two ways of doing it. You can say that they are so much bigger than it that you can approximate that to be just the H plus from reaction 1. It's an approximation, so they might not give you the exact answer, but you'll be very close to the exact answer, as this thing will be very small compared to the H plus that got dissociated from reaction 1. If I look at reaction 1, so this is not option A, this is just like, let's say step 1. Maybe I just do first step, okay? So let's look at reaction 1. So what is going to be our concentration of H plus here? Remember that all of this is in the same total volume. So if I started off with 2.00 mole per dm cube, therefore I will expect 2.00 mole of H plus, because 1 mole give you 1 mole, 1 mole give you 1 mole. So the mole of H plus is going to be equal to the mole of H2SO4 from reaction 1. So therefore the concentration of H plus equal to the concentration of H2SO4, because they are in the same total volume. So that will give me 2 mole per dm cube. Remember that this H plus is the total H plus present, not just from here, but also this concentration plus this concentration. But because of our approximation, that's going to be similar or very close to this big amount, which is much bigger than the amount from the equilibrium itself. So our second step in reaction 2, so what we have is we have the concentration of HSO4 minus to be 1.988 mole per dm cube. But remember that this is in equilibrium, so not all of them dissociate. Not all of them dissociate. If not all of them dissociate, you're going to get a very small amount of these, which is why this approximation works. Okay, so in terms of that, since I know the amount of these, and what else? I started from a 2.00 mole of that as well, because remember that 2 molar, give me 2 molar, but at equilibrium, I only have this much mole per dm cube. That means from here to here, how much has reacted? How much has reacted? That is very, very important. So if I think about from 2 molar to 1.988, so the mole of HSO4 minus reacted is going to be 2.00 minus 1.988, and that will give me 0.012 mole, and they are in the same volume. Remember, all of these, they are dissociation in this from the same total volume in the same solution. So the total volume is the same, so therefore the concentration of HSO4 minus reacted is going to be 0.012 mole. From your second equation, if this much reacted, then you will get that much and that much, because not all of them reacted, only this much reacted. You're left with this at equilibrium. How much of this you have at equilibrium and how much of this you have at equilibrium. So therefore the mole of SO4 2 minus, therefore the concentration of SO4 2 minus at equilibrium is equal to 0.012 mole, because 1 mole of it comes from 1 mole of this that reacted. So 0.012 mole of this is reacted, you have 0.012 mole of it. You also have 0.012 mole of these. I've done this approximation, but what you could do is you could add 2.00 plus the 0.012. So the H plus at equilibrium by right is 2.00 from the first dissociation. They give you this already, but from the second dissociation you get 0.012. So as you could see, it almost makes no difference at all. Yeah, there's concentration that I'm talking about, so they are mole per dm cube. This should be mole per dm cube as well. That should be mole per dm cube as well, remembering that they're all in the same volume. So I could sub all of this into my Kc expression, which is Hs of, well, I've got the expression on top there. I'll just copy paste it. Remember that in the multiple choice, you really only have 1 minute for each question. So I've actually spent a lot more time on these just to try and get you to see the underlying concept. But there's where the 0.012 comes in. That's where this 2.012 comes in. And then you get the amount of HSO4 minus present in equilibrium. This is how much reacted, but how much is present in equilibrium? 1.988. So you need to be very careful. Pop that into your calculator and you will get Kc equal to 1.214 times 10 to the minus 2 mole per dm cube, because the unit of mole per dm cube times mole per dm cube over mole per dm cube cancel out to mole per dm cube, and this is option C for that question 10. Question 11 is about autocatalysis. So autocatalysis is something that is covered in more detail in A2 kinetics, but it's also something that you will have learned in AS depending on your teacher. But regardless, you know, like the question actually tells you what it is. They say the products catalyze the reaction. The products catalyze the reaction. So as we produce the product, so as the reaction makes product, and your products will speed up the reaction, therefore reaction get faster. But then there's the first aspect of it. When reactant is nearly used up, when reactants nearly get used up, so meaning to say you don't have much more reactant, doesn't matter whether you have more products and therefore more catalysts, but reaction will slow down because you don't have a lot more products, and you don't have a lot more reactants because they are nearly used up, therefore they will slow down towards the end. So this graph that they want you to think about is rate against time, so you need to be very careful. So this is rate against time. There's actually a different graph which is to do with concentration against time. So I'll plot a different graph which is not given there. So if I have, let me see if I have a straight line. No, I don't have a straight line. It's like, let me see if I can do a bit better. Drawing the screen is a bit, well, there's pro and con to it. So if this is my concentration of products, let's say, you could do concentration of reactants. These two graphs are clearly different because even though the x-axis is the same, the y-axis is different. Rate is to do with change in concentration over change in time. There's your O-level or IGCSE definition. This is concentration of products. Initially, I will have no products. So no products to start with. And then my reaction will get so fast that my product is being produced at a much faster rate compared to initially. Initially my rate of reaction is like this, where the change in concentration over change in time is the rate of reaction, and then I would have the rate getting faster because the product catalyzed the reaction, so it makes the reaction faster and therefore giving me more products. But towards the end, I will slow down again. Oops, I don't want that. No, I want that. Never mind. So towards the end, it will slow down again and there'll be no more product produced as reaction finishes. Now let's have a look at the gradient again. So the reaction gotten so fast there, and then the reaction slows down again. This is the idea of concentration against time for an autocatalysis reaction. For an autocatalytic reaction, or we call it autocatalysis. On the other hand, we can see that the rate is slow, and then the rate increases, and then the rate comes down. So in terms of the rate increases, and then the rate comes down. Okay, so going on to the answer, this is very obvious that this is option C. It cannot be option D. D cannot be, because if you look at option D, there is no increase in rate. That's how you know that there's no autocatalysis. If you look at A and B, this looks like B. Okay, this option here looks like B, but for B, this is concentrations over time. This is not rate over time. So let's try to trick students who can't read the y-axis at all. It can't be A, because A, the rate increases, but the rate does not decrease. And it doesn't make sense that the rate sustains itself forever, because your reactant will get used up eventually. So the only best option there is C and not B. Careful with B. It looks like this graph, but this is a concentration against time. This is not rate against time. Moving on to the next question, 12. So X and Y are two elements. So these are period 3 elements. You have X and Y. They combine, so X plus Y give you Z. And this Z will dissolve in water, so plus water, you will get acidic oxide. And this thing has an X in +4 oxidation state. How about Y? Y will give you amphoteric oxide. So if you think about amphoteric oxide of period 3, this is your case study. This is Al2O3, therefore Y is aluminium. So this means C and D are out. So you're left with between A and B. So what can we say? A is phosphorus, B is sulfur. So let's think about this. These are acidic oxides, so they are of non-metals. So phosphorus, sulfur, yes and yes. How about this X plus 4? Then you think about the oxide that has +4 oxidation state. Then you think about P4O6, P4O10. P4O6 is going to be phosphorus +3. P4O10 is going to be phosphorus +5. So that can't be the case at all, which means it must be sulfur, where you have SO2, there's sulfur +4, versus SO3, there's sulfur +6. Which means we are looking at that +4 oxidation state as the next bit of important information. So therefore X is sulfur. So we have Y, handwriting is getting really bad here. Y is aluminium, X is sulfur, so you only have one answer, which is B there. Aluminium sulfite, Al2S3. As you can imagine, an ionic compound, Al3 plus and S2 minus. You have learned the recombination of ions is to do with the valency, their combining power. This is to do with this cross multiply method, but it's actually lowest common multiple. Lowest common multiple of the charges brings down to +6 and -6. So I'll bring down the number, which is 2. I bring down the number, which is 3. This means 2Al3 plus will combine with 3S2 minus. So altogether I have Al3 plus 2 of them and S2 minus 3 of them. This simplified to Al2S3, and that is option B there. Question 13. So this is about two elements in group 2. So straight away we know that this is group 2 chemistry. Group 2 chemistry, Q and R, doesn't matter. They say 3 statements are correct. 3 statements correct for Q. The remaining meaning the other one. The remaining statement is correct for R. So you're looking for the remaining statement, the one where it only applies for R. Careful, yeah? So they are all correct statement, but 3 are correct for Q and only 1 is correct for R. So let's see. So group 2 elements, what do we have? We have beryllium, magnesium, calcium, strontium, barium, and radium, I guess. Radium all the way down there. Which statement applies to R? Let me think. The first one is talking about hydroxide. So A is talking about the OH minus. So I need to know about the solubility of the hydroxide. So the solubility of the group 2 hydroxide will become more alkaline down group 2 as the cation gets bigger, as you have more shells. So this is more alkaline. More alkaline because it is more soluble. So therefore, more alkaline, your pH is going to be higher, closer to 14. Think about it, barium hydroxide is going to be pH 14, magnesium hydroxide is only around pH 9, give or take. The other one is you have a carbonate used in agriculture to reduce acidity of soil. So we're looking at calcium carbonate here. So blah, 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 blah. Reduce soil acidity. So we know that this is a chemistry of calcium. So calcium carbonate is used to reduce soil acidity because they specifically say carbonate. Calcium 2 plus, CO3 2 minus. Now in terms of C, I hope you can see that your atomic radius going down the group, well, I probably don't need to draw a graph. You can hopefully see that going down the group. Down group 2, you have more shells. Therefore, radius or atomic radius increases because you have more shells. Now for D, it reacts more quickly with cold water. So when you have metal M from group 2 reacts with cold water, they should give you metal hydroxide if this is liquid and this is solid, and this should give you aqueous and H2. So balancing equation should give you that. And this is only assuming it's a reactive metal and it's reacting with liquid water. Obviously things like magnesium doesn't react with cold water, but magnesium can react with steam, and steam is not liquid water. As this one is water, and it's a reaction with cold water. We need to think in terms of the redox. So this is this is a redox reaction definitely. So this is H plus 1 and this is H0. So in this redox reaction, what we see is the metal has to lose electron, lose the 2 valence electrons. As a result of it, going down the group, you will expect that they are easier to lose the electrons going down to group 2 because the valence electrons are further and further away from the nucleus, and therefore they are more shielded and therefore much easier to be lost, and therefore much more reactive group 2 metal going down group 2. Let's see. Perhaps I should really copy that. I think I keep on making this mistake. I should really start from a new page for each and every new multiple choice questions to avoid ever running out of space like this. All right. Yeah, move that a little bit there. Okay, so what can we say now? So between A, B, C, and D, 3 statements are correct for Q. So if this is talking about calcium, if this is definitely calcium, then let's think about, if this is calcium, then a saturated solution, this question is a bit tricky. I probably want to omit beryllium and radium, partly because beryllium chemistry is leaning more towards covalent. Radium is more radioactive, so we can be thinking about these 4 things. My head is spinning now. Which statement applies to R? I wonder what's the best way to explain this now. Let's see. Okay, let's say we start from assuming this is calcium. So we know this is true. Okay, we know this is calcium carbonate. Now calcium carbonate is used to reduce soil acidity. Calcium hydroxide compares to, all right, so we know from B, our point of view is calcium. Okay, so we can either compare magnesium or barium. Okay, so we do quite a lot of barium chemistry and magnesium chemistry. We don't really do a lot of strontium chemistry. You could compare strontium here if you want to. It's really up to you. Let's think about the hydroxide, right? If this is Q, then B is correct. So B is correct. Then you have magnesium hydroxide and you have barium hydroxide. So what is the other metal that would have higher pH value? Then it will be calcium and barium, because from that thing there, it says if this is Q, then 3 statements would be correct. So barium will be more alkaline than calcium hydroxide. So therefore, A is correct for that. A will be correct if the R is barium. Okay. Now barium. So if this is Q, then this is R. Then we are saying that A is correct. B is correct. How about C? C is talking about calcium 2 plus, atom. So we're talking about barium versus calcium atom. So this metal R has the greater atomic radius, so that is correct. This metal R reacts more quickly with cold water. If this is barium, if this is R, barium is more reactive than calcium with cold water. So what does that tell us? That tells us that if it is barium, then A is correct, B is correct, C is correct, and D is correct. So all 4 are correct. If this is Q and if this is R, all 4 are correct. But if you look back at the instructions, supposedly only 3 are correct. Okay, only 3 are correct. I hate this question. There's a lot of wording. Only 3 are correct for Q. But all of these are correct for Q if it is this. And therefore, what I can say is perhaps Q cannot be calcium. Perhaps Q can be barium. Maybe. Could it be the other way around? As in, at the moment, Q is above R. So what we are saying is, if this is true, Q is above R. Alright? So now we want something where it's not all of them correct. But here all of them are correct when Q is above R. So what we are saying is, therefore, Q is below R. What would happen if Q is below R? If Q is below R, then this must be the new R. So what can we say? If we have magnesium as the R, and calcium as the Q, then a saturated solution of R will be more alkaline. Is that correct? A saturated solution of R will be less alkaline than Q, because pH of the alkaline solution Remember that if you have magnesium versus calcium hydroxide, magnesium hydroxide, the new R will be less alkaline than the calcium hydroxide. So A will be wrong. B will still be correct because we still use calcium carbonate to reduce acidity of swell. But R will be smaller in radius than calcium for the atom. And R would not react quicker than cold water. In fact, it doesn't react with cold water at all. I just mentioned that when I talk about magnesium, only reacts with steam, which is H2 in the gaseous state. So this must be wrong. So what we said earlier, Q is above R must be wrong. Q is below R must be correct. So therefore, option B is the one that will apply to R in order to satisfy the condition that three are correct. Three statements are correct for Q, but then only one is correct for metal R. Okay, am I correct? I don't know. The one remaining statement is correct for metal R. Let me see what am I talking about. Then we can definitely say that they say one remaining statement is correct for metal R. So if we say this is calcium, then we say that R is calcium. Then we think about the other three statements being correct for, sorry, if this is metal R, the three other statements are correct for metal Q. The other three statements in metal Q. Let's think about where we will put our calcium. Our calcium will be there. Then if there's our calcium there, you want the saturated solution of the hydroxide to have the higher pH value. So we are looking at something which is around that area, something which is below calcium, so something around that. Okay, so we have to be thinking about the three remaining statements for Q as the element below calcium, therefore more soluble hydroxide, therefore bigger atomic radius, therefore easier to lose the outer shell electrons. Alright, that can only be true if B is the option, and therefore that is why B is the statement that will apply to R, and these are the three statements that will apply to Q. They will be correct. In question 14, so we have electronic configuration, is also known as electronic arrangement. These are atoms. We're looking for the strongest. So the idea is strongest, and you also have the other idea, which is oxidizing agent. So these are elements. So element, I don't know why it's acting up now. Oxidizing agent. So oxidizing agent oxidizes the other substance. So they oxidizes other substance, and what happened to its surface is its surface get reduced. So we have to look at this configuration and try to make sense of it. You have 1s2, 2s2, 2p5. This is actually a group 17. In period 2, there is your fluorine. It's a fluorine atom, by the way. But then, they say element. The element will be F2 because they say which element is the strongest oxidizing agent. In fact, there's our answer already, as you know from the group 17 chemistry, that from fluorine, chlorine, bromine, iodine, so they are stronger oxidizing agent. So stronger oxidizing agent because they like to gain electrons, they like to be reduced. Fluorine, being the most electronegative atom, really wants to do that. So we can be sure that that is our answer already. But when you look at B and also D, you can hopefully see that, you know, these are metals. This is a group 2 metal. And if I look at D, I have another group 2 metal, so 2p6, 3s2, 3p6, 4s2. So this is again a group 2 metal. So metal likes to lose electrons. So metal has that tendency to lose electrons, therefore they're electropositive, therefore they are good reducing agent because they like to get oxidized. They like to get oxidized, okay? They like to lose electrons, they like to get oxidized, they are good reducing agents, and therefore they cannot be good oxidizing agents. Between A and also option C is actually, well, if I start from neon and I have 3s2 and 3p5, I will have group 17, but in period 3, so there's chlorine and there's CO2 element. This goes back to this idea of the strength of the element as an oxidizing agent. It prefers to gain electrons more and more, going up the halogens, and therefore this is the stronger oxidizing agent. A is the correct answer and not C. Question 15. So what we have is, these are separate test tube reactions. If you look at calcium with water, so they say excess calcium with water. So magnesium doesn't react with cold water, but calcium can react very, very slowly with water, and you use excess calcium. You're going to get calcium hydroxide plus hydrogen, and that should be balanced out like this. And we know that calcium hydroxide is not very soluble in water. In fact, it gets saturated. Saturated solution of calcium hydroxide is what you call lime water, and they're not very soluble in water at all. So that should be your white precipitate. And then number 2, this is BaCl2. Well, they give you barium chloride. You should be able to write down the formula. So with the exchange of ions, you're going to get barium hydroxide and strontium chloride like that. Well, barium hydroxide is definitely soluble because it's a very, very alkaline solution. Strontium chloride, just like the rest of the group 2 chlorides, they are soluble. So group 2 chlorides are soluble. There are only a couple of chloride that are not soluble, which include silver chloride and lead 2 chloride. So 2 is definitely out. If you look at number 3, you have calcium carbonate plus excess HCl. So that means when you get the salt, again, group 2 chlorides are going to be soluble. And then you get CO2 and also H2O as the byproduct. But don't forget, you also have excess unreacted HCl, which of course we don't write in the balance equation because, you know, stoichiometrically all the HCl will be used up in the balance equation, but we know that it's only the remaining HCl that are unreacted that remains and not the solid. So we will not see this white precipitate, will not see this residue at all because we know that that is insoluble in water. However, be careful. With excess HCl, this will completely react, so we will not get any of that. This is a gas, this is a colorless liquid, this is soluble in water. Group 2 chlorides are soluble in water. How about reaction number 4? Reaction number 4 is a magnesium sulfate. When I add it with barium nitrate, I'm making exchange of ions, so all nitrates are soluble, magnesium nitrate no problem. Barium sulfate, this is a key test for sulfate ions. This is a white PPT, a white solid that is very insoluble in water. So the solubility of the sulfate actually decreases. It becomes less soluble down group 2. So this definitely will produce a white solid product. Okay, so option 1 and option 4 are correct. So there are 2 out of 4. So it must be option C there. Question 16. So this is going back to the idea of which compound does corn sulfuric acid. So this is corn sulfuric acid plus the halogen. So if you know corn sulfuric acid plus the halogen, like, I don't know, X minus, so the halide, not the halogen, what you will get is you will get HSO4 minus as the ion. After you donate the H plus, you get HX. This is what you call an acid-base reaction. It happens with Cl minus, happens with Br minus, happens with I minus. Alright, but then the other thing is redox reaction with Cl minus, no reaction, because, well, there's the extent of it. So this is the oxidizing power of the halogen, so chlorine, bromine, and iodine, and corn sulfuric acid comes somewhere in between there. So corn sulfuric acid cannot oxidize chloride to chlorine, but it can oxidize bromide to bromine, it can oxidize iodide to iodine. And remember that in this product, simply an acid-base reaction product, you still have X minus 1 oxidation state, so there's no redox there. But with Br minus, you will get Br2, which is a redox product, and then you will get SO2, which is a sulfur plus 4 oxidation state, and it will stop here. This is part of your AS Group 17 case study. If I use a different color to represent the other reaction that I want to show you, so with I minus, you will get I2, which is iodine 0 oxidation state, but you will get various other sulfur product, which include elemental sulfur, which is sulfur 0. So this is elemental sulfur. It's going to come out as a yellow solid. If you have never seen a yellow sulfur before, and it will not stop there. In fact, it goes all the way to H2S, which is hydrogen sulfide. Hydrogen sulfide has a rotten egg smell, so this is your rotten egg smelling gas, which is your H2S or hydrogen sulfide, which is a redox product because it goes from consulfuric acid where the sulfur is plus 6 oxidation state, and you're just donating a proton. This hydrogen sulfate ion is also sulfur plus 6, but these are reduction products. So with which compound does consulfuric acid react both as a strong acid? The first reaction is as a strong acid, as a proton donor. Proton donor, because it's acting as an acid. There's a definition of acid for all level IGCSE chemistry, and we can see that reacts with bromide. So it has to be the bromide that actually result in both the acid-base reaction as well as the redox reactions. So therefore, we are looking at option C and not any of the other option. Question 17. So there's some more acid-base reaction, but it is to do with ammonia. So if we have an equation NH3 plus HCl, we will get NH4Cl. This is actually NH4 plus Cl minus. In terms of diagram, you should be able to draw things like this, where you have lone pair, you've got 3 bond pair and 1 lone pair. From your AS chemistry, bond pair, lone pair repel more than bond pair. You will get trigonal pyramidal geometry, not chemistry, and this will be 107 degree. And you get H plus and Cl minus. Well, sorry, it's hydrogen chloride, it's not HCl aqueous, so it's actually HCl like this. This is delta plus and delta minus, and what actually happened is you will get lone pair, dative covalent bond to the other H plus, and the other H plus now has 2 electrons from the nitrogen, giving you a plus charge transfer to the nitrogen, now with 4 covalent bond, and this now has 4 bond pair and 0 lone pair. So the 4 bond pair repel equally, and now you get a tetrahedral geometry with 109 degree bond angle. And the chloride is not bonded directly to the nitrogen because nitrogen is a second period element that can only accommodate 2, 4, 6, 8 maximum in the second shell, and it cannot form more than 4 covalent bond essentially. Now when you look at that, they say ammonium ion is basic. Well, normal lone pair. When you have normal lone pair, not basic, because you cannot pick up another H plus because you have normal lone pair to do that. So option A is wrong. Okay. How about option B? The hydrogen atom from HCl donates. There is no hydrogen there's no electrons on this H plus at all. In fact, this is the donor, this is the acceptor. If I label it very clearly, this is the donor and that is the acceptor. Electron pair donor, electron pair acceptor. So that is the acceptor, and therefore option B is definitely wrong. Now talking about the bond angle, so I've written on 109, some books will say 109.5, whichever one you use would have been okay. So in ammonia it's 107, now it's 109 in the ammonium ion, so clearly they are not the same. So in terms of the bond, that is bond angle. In terms of the bond angle, option C, that is definitely wrong. So we are just looking at option D as the only correct answer, because if you think about it, 4 bond pair and 0 lone pair, that looks exactly like in a methane molecule where you got 4 bond pair and 0 lone pair, and therefore 109 degree there. Question 18. So we have some more group 2 chemistry. So this is about the temperature decomposition. So how easy it is to decompose. So in fact, going down the group 2, the thermal stability of the group 2 carbonate increases as the group 2 cations become bigger in size. They become more stable to heat. If they are more stable to heat, more difficult to decompose, so not as easy. So more difficult to decompose. If you are more difficult to decompose, your temperature of decomposition will increase. Therefore, we're looking at option C or D. A and B are out. In terms of first ionization energy, down the group, you should be able to prepare an assay for these. You have more shells, and therefore we talk about the valence electrons are more shielded. Despite the increase in nuclear charge, this more shielding is very important, that your effective nuclear charge decreases down the group. This effective nuclear charge is basically the net effect that your valence electrons feel for the protons in the nucleus. How are they attracted? And since that is becoming lower, therefore easier to lose the valence electron, because they are not as attracted as those valence electrons for the elements that are higher up in the group with lesser inner shells. So we're looking at first ionization energy decreases because easier to lose the electrons. Therefore, first IE, I should really write a lot better. So the first ionization energy decreases. So what does that give you? Just now was C or D. Now you have first ionization energy decrease. So we're looking at option D as the only correct answer. Option D there. Question 19. Hope this is a short one. Don't want to move on to the new page. SO2 reacts with calcium hydroxide. So SO2 is an acidic oxide. It reacts with calcium hydroxide. So Ca2 plus OH minus. So you need 2 of the OH minus in the bracket. So this is a base, or you can think of it as an alkaline. It will give you a salt. The salt that you get from SO2 is what you call a sulfite with ITE, because that is going to be SO3 2 minus, where the sulfur is a +4 oxidation state, just like it's a +4 oxidation state here, because an acid-base neutralization is not a redox. It is not a redox, and therefore you do not have a change in oxidation number. You must produce SO3 2 minus. A lot of students will have had a very difficult time when they start producing the SO4 2 minus, which is the sulfate that will come from SO3. So Ca2 plus SO3 2 minus, that will give you CaSO3, calcium sulfite, alright, and that will give you water as well. So balancing that equation, I got 2 water. Nope, I just only have 1 water. So 2 hydrogen, 2 oxygen, 1 goes there, 1 goes there. Everything is balanced just like that. So what is the main product there? So this is the main product. So therefore, there's option C there. You can be thinking about this is a flue gas desulphurization. This is something that was covered previously in, I want to use a different color ink. Previously covered in O-level or in GCSE or IGCSE syllabus under environmental chemistry. You want to remove SO2 as a gas. You react it with this with this basic oxide. Even you can use calcium oxide if I'm not mistaken. So you can use SO2 plus this calcium oxide and it will give you CaSO3. This is a solid. You can use it as a solid and a gas. This is easy to remove because when it is a solid you can just filter it off. This one difficult to remove. You can't really remove gases easily, so you react with something to produce a giant ionic solid, calcium 2 plus, SO3 2 minus. This is what you call, I forgot what is this one called already. Is this one called slag? No, slag is something different, sorry. This is flue gas desulphurization technique. SO3 2 minus, the salt that you get from SO2 in the same oxidation state, sulfur plus 4. Question 20. So what we have is we need to consider structural and also stereoisomerism. So be very careful about this kind of question. Alright, so if I have X and I have HR and then this thing is pointing away from you behind the screen, and this thing is coming out and pointing at you right in the eye. Y is going to be HO like this, and now the H is coming out towards you and the Cl is pointing away from you, and Z is, well, this thing here. Okay, so how many other isomers? So a couple of things to note. They want other isomers, so excluding these three. They also want something which is alcohols. Okay, so let's try and see. So there's a chiral center there, so that's already provided for you. C3H7ClO. So they want C3H7ClO. So all of these are 3 carbon, 3 hydrogen, 4, 5, 6, 7. So that how many other isomers are there that are alcohols? Well, let me think. What I could do is I could have HO like this, I could have Cl, and this would be chiral because the carbon there is bonded to Cl, something with OH and a CH3 and a H. So this will give me 2 stereoisomers. In particular, in fact, 2 optical isomers because I have 1 chiral center. Optical isomers, not optical center. So I'll have 2 isomers there, extra thing in green. I wonder what other thing I can draw. So that chlorine is on the same position as OH. So there's 1, 2, and 3. This is 1, 2, and 3. I could then move the chlorine onto position 3. Like this. So 1, 2, and 3. You could also think of it as 1, 2, and 3, I guess. But we are not concerned about naming here. So I get 2 and another 1. What else can I do? So the HO is the same as Cl position. HO and Cl are different. HO and Cl are different. This is Cl and OH on the same middle carbon. This is HO and Cl on the terminal carbon. What else can I do? Well, this one, hopefully you can see that, you know, the HO and the Cl are like this, which means you can have a different partner, which is where the Cl is terminal and the OH is there. This will be different from this because the OH is in the middle, and you also have a chiral center. So another chiral center. Therefore, 2 optical isomers, which, you know, comes under stereoisomerism. So I got 2, 2, and 1. So altogether, 2 plus 2 plus 1 is equal to 5 other stereoisomers and the structural isomers. Right, so this is just a position isomers where you could see the HO and Cl are on the same carbon. The HO and Cl are on the same carbon. The HO and Cl are on different carbon. The HO and the Cl are on different carbon. The HO and Cl are on different carbon, but I just swap them around. Each pair will give me, well, each optical center will give me 2 pairs. 1 pair, meaning 2 optical isomers. Okay, so I get 5 other. That's what they wanted. How many other isomers? They didn't say, including itself. So this must be option D. Question 21. So 2 students make a statement. 2-methyl bit 1 in. So 1, 2, 3, 4 is a bit 1 in. So it's an alkene at position 1 there. And it's a 2-methyl. So it's a 2-methyl bit 1 in. Student 1 states that one has a geometrical isomer. So this one has carbon-carbon double bond. But I can tell you no cis or trans, meaning geometric isomers. And the reason for it is because you have 2 groups, there's CH2 there. So because terminal CH2, you got a hydrogen and hydrogen, means 2 same atoms or 2 same groups of atoms on the same carbon, of the carbon-carbon double bond. Therefore, no cis trans or no geometric isomerism is possible as a result of that particular condition that's imposed by cis trans isomerism. So student 1 must be wrong. So student 1 is wrong. So if you look at which students are correct, so both 1 and 2 are correct, 1 only is correct. So therefore, A and B is definitely out. You're just left with C and D. So let's have a look at student 2. So it says that reacts with HBr to give 1-bromo 2-methyl-butane as the main product. So I'm going to try and react that with HBr. So I will get, well, I can get the H there and the Br there, or I can get the H there and the Br there. So what I'll get is I can get Br there if I add a H there. Or actually, let me just try and draw it on another at the bottom there, because I got quite a lot of space, so that is a lot easier to explain. Let's see, if I erase that first of all. Okay, so remember in the mechanism, so this question is not asking you a mechanism, but it's really good exercise to draw from the double bond, attack the H, the rich attack the poor, kick out that Br minus. Then what you get is you can get these where the H adds there, and then you have a plus on the other side of the carbon. You can find more about this in my electrophilic addition part 1 and part 2 tutorial video in the A-level concept tutorial playlist that was never deleted, even when I deleted quite a lot of my copyrighted tutorial videos. Those A-level concept tutorial videos were never deleted, and there will be a very good tutorials for all of your A-levels organic mechanism. I've added the H there, and I get the plus charge, the carboxyl ion on the other carbon. Now I could add the other hydrogen on this side, and I could get a plus charge there. If my plus charge is there, and my plus charge is there, this plus charge, the carboxyl ion, is bonded to 1, 2, and 3 other carbon. This is what you call a tertiary carbocation. And the other one is what you call a primary carbocation, because the carbon with a positive charge is bonded to 1 other carbon. So that is primary carbocation. Tertiary carbocation is more stabilized. So you say more stabilized by more electron donating groups. These are asked in theory papers, by more electron donating groups via inductive effect. So since they're electron donating, they help to stabilize the electron deficient center, and therefore it's a stabilization effect. As a result of it, I can then use my Br minus, showing the lone pair, attack the carbon there. Br minus, showing the lone pair, attacks the carbon there. So tertiary carbocation will give me, tertiary carbocation will give me the tertiary halogenalkane, and the other one will be like this, and then the Br there. This is going to be a tertiary halogenalkane and a primary halogenalkane. As a result of the same explanation, the carbon with the halogen is bonded to 1 other carbon. The carbon with the halogen is bonded to 3 other carbon, and this will be your major product. With respect to this particular question, this is a multiple choice question. Do I really want to draw the mechanism for that 1 mark? No, you can take a shortcut, but this mechanism is simply there, to help you understand what's going on. This is 1, 2, 3, and 4. So this is actually what you would say. This is 2-bromo, 2-methyl-butane, and that is your major product. So that's how I know student 2 is also wrong. Since student 1 was wrong, and now we know that this comes from the tertiary carbocation, which is more stable than this intermediate. Therefore, this is the major product. This is named as 2-bromo 2-methyl-butane, and that's the major product. So now we know, therefore, neither 1 nor 2 are correct, because the question is asking you which one is correct. So this is option D there. Okay, and this other product is 1-bromo 2-methyl-butane. Now going back to what I said about what shortcut can you take. Okay, one of the shortcut you can take, I guess, is you say this one, Okay, and you say that based on the question, so this is what the question said. The question says 1 bromo 2 methyl butane, right? So you will draw butane. 1 bromo 2 methyl. So if the question say like this as the major product, then I'll cut it, I will fragment it, I work backward, then I will get this. This is a primary carbocation. This is a primary carbocation because the carbon with the positive charge is bonded to one other carbon. And we know that this is not very stable compared to putting the plus charge on the other side, and therefore this cannot be major product. Therefore, not major. And the question says is the main product, so that's how I know student 2 is incorrect, just from this, kind of shortcut, I guess, just based on information given in the question. Or in the theory paper, they ask you to explain with the use of mechanism why this is the major product and not this one. Well, you'll be able to explain all these in detail and not just choosing A, B, C, or D. In the next question, 22, so which statement is correct when you are referring to complete combustion? So we're talking about complete combustion, so that means in excess oxygen. And we're talking about PVC, which actually stands for polyvinyl chloroethene. So your monomer consists of this. This is your monomer. And therefore your polymer consists of this, which is basically PVC. Or you can draw it like this, where it's open chain and then H and Cl. Doesn't matter where you put the Cl because these are all single bonds, so you can rotate about the single bond. Now you say complete combustion, they talk about you can cross out option D because first of all you got this chlorine. I don't want that. I want to use a bit of pink. So you got toxic gases, which could be HCl example. Alright, so they say option D is definitely wrong. How about option C? If water is used to clean the exhaust gases, the water become alkaline. This is option C is also wrong because this is acidic gas. So not only is toxic, it's also acidic. So C and D are definitely wrong. Carbon dioxide and water are the only products. Well, you can also get HCl because you have Cl as an external atom in addition to carbon and hydrogen. It's not just a hydrocarbon polymer, it's also containing chlorine. So you cannot get carbon dioxide and water as the only containing products. So, oh no, I accidentally passed that, never mind. I don't know why I can't, let me see if I can, okay, I can get rid of it now. Alright, never mind, acidic gases, so I can also cross out option B because I don't want to circle that, otherwise it confuse you, because HCl also forms. So therefore, out of all that option A is the only correct answer. The gas which contributes to global warming comes from CO2. It's got nothing to do with chlorine, but I can tell it that's the answer because all the other three options are incorrect. Question 23. So I have iodoethane. So iodoethane is CH3, CH2I like this. And then I will react it with aqueous. So the idea is aqueous, AgNO3. The Ag plus or the NO3 minus is not the nucleophile. It's actually the water that is the nucleophile. It's got the lone pair on the oxygen, attacks the carbon, and then kick out the I minus. And then after a few steps, well, 1 or 2 steps, then you can get the OH, the alcohol, as the product. This is the hydrolysis product because you are breaking the carbon halogen bond with the use of aqueous conditions, whether it's OH minus or H2 acting as a nucleophile, you're still going to break the carbon halogen bond. This is hydrolysis of the carbon halogen bond. This is a hydrolysis product, but you also kick out I minus, which can recombine with Ag plus, and this will be a yellow precipitate because, as you know, Ag plus I minus, very, very popular ionic equation to show the precipitation reaction ever since you were in O-level or IGCSE syllabus. So this is a hydrolysis type of reaction, but the mechanism, as I have drawn it, is the nucleophile coming from the water in the aqueous solution attacking the electrophile. Rich attack poor, nucleophile attacks electrophile. Altogether, I have substituted the iodine with OH. So this is nucleophilic substitution. This is going to be a yellow PPT, which means your only answer has to be option D there. Question 24. So we convert iodopropane. So this is 1, 2, and 3. And we convert into butanoic acid. 1, 2, 3, 4. So there's 1, 2, 3, 4. 3 carbon into 4 carbon. We need to add carbon. So you need to think about adding carbon. One of the way of adding carbon is using Cn. So this is a nitrile. This is called butane nitrile, because start from there. 1, 2, 3, 4 is a nitrile, and there are 4 carbon, butane nitrile. The question now is, it's not direct, it's actually 2-step. So when you want to add carbon, we would use KCN because we are doing nucleophilic substitution of a halogenol alkane to nitrile. So KCN in ethanol. And you also need a reflux condition. On the other side, this is your hydrolysis. Hydrolysis of nitriles. You would just need a dilute HCl or dilute H2SO4, and you need to reflux it, and you can get the nitrile off to become carboxylic acid. So very clearly, this question is asking you on this side, which is adding carbon. So it must be option C. It cannot be option A or B or D because add carbon. There's a strategy there. 3 carbon to 4 carbon. Question 25, you got to think about is this a 1-step or is this a 2-step reaction? If this is a 1-step reaction, then it will proceed via transition state. Transition state is how you define as like a single hump in the reaction profile diagram. So instead, when you have a 2-step or a multi-step reaction, what you will get is you will go via an intermediate. Okay, so this intermediate could be carbocation, could be carboanion, could be radical. So if I just say carbocation, carboanion, or even oxyanion, or even radical species with unpaired electrons, and this will be multi-hump. Typically, it looks like a double hump. Example, double hump, meaning like a McDonald's kind of reaction profile diagram. So here you have a multi-hump, which is essentially what I just said. So you have E, and you have, what is it, going up, and then going down, and then like this. So this thing here, Z, that is your intermediate, and these are your transition state. So there are more than one transition state because it proceeds via 2-step. So this is your first step, and this is your second step. So they are telling you in this reaction that they give you is a, well, cyclic compound, but it's a CH3 there and a Cl. The carbon with the halogen is bonded to 1, 2, and 3 other carbon. This is a tertiary halogenol alkane. When it reacts with that, it doesn't go straight away because it's not an SN2. Instead, what it does is you draw a dipole first, and then what happens is you will kick out. This is called heterolytic fission. 2 electrons in that bond just go to the chlorine, and you will get a carbocation. This is called tertiary carbocation intermediate. And that's the dip in that reaction profile diagram, and you get Cl minus like this. So what happened with this intermediate in the second step is that the hydroxide will then attack the carbon. The hydroxide does not attack the plus, it attacks the carbon because you are forming bond. So you are forming bond between the carbon and the OH, just like that. So this is the slow step. This is the rate determining step. It will make more sense in A2 rate of reaction. This is the fast step. This is the first step. This is second step. this is called Sn1 mechanism because there's only one molecule involved in the slower step of the reaction. There's only one molecule that involved in the rate determining step, which is the slow step of the reaction. So rate is equal to rate constant multiplied by the concentration of the tertiary halogenyl-alkane. More of this in A2 rate of reaction topic. Anyway, this is the intermediate for this particular reaction. So it has a plus charge. It's not a delta plus. Delta plus would mean partial charges. This is a full carbocation intermediate. So altogether, you can summarize that what I've just told you. Option D is definitely the correct option there. So moving on to this question 26, what we have is an alcohol. So this alcohol is C5H12O. First of all, it decolorizes, meaning to say it turns to colorless. This warm acidified potassium manganate 7. Potassium manganate 7 is manganese plus 7. It's a deep purple color, and it will go to manganese plus 2, and the species will be Mn2 plus aqueous. The oxidation state of these pale pink / colorless species is a result of the manganate 7, meaning to say the Mn plus 7 acting as a oxidizing agent, meaning to say this thing can be oxidized. So your conclusion from this is this thing can be oxidized by KMnO4. That's why KMnO4 acidified turns from purple to colorless or pale pink as a result of it. Onto your second point, we also said that it turns, it gives with alkaline aqueous iodine. So alkaline meaning in a OH minus environment. Aqueous iodine is just I2 in water. So it's just aqueous, I guess. If I write aqueous already in front, I don't need to. I get a yellow precipitate. This precipitate is something you call iodoform. Iodoform is triiodomethane. That is the official name, triiodomethane. It's a classic test. It's actually a very, very old test. It's a test to confirm CH3C double bond O. So it's what is used to test for methyl ketone or N. You will see in the syllabus under alcohol where you can have CH3CHOH. It's used to test for this in alcohol topic. It's used to test for this in the carbonyl topic. Together, these two topics to combined, you should know it's to use to test for this as well as this. So it could be this or this. From all the options given, none of them is the methyl ketone. So none of the option is a ketone. A, B, C, D, they are all alcohol. So we are realistically looking for these based on the option given. So let's have a look through the options. So option A, you have 2-methyl butane 2-ol. So if we have 2-methyl butane 2-ol, the first thing we do is we look at the butane, which is 4 carbon. So there's 1, 2, 3, 4. You have a 2-ol, so it's a OH there. You have a 2-methyl, so it's another CH3 at position 2 there. So what we can say is, hopefully you can see the carbon with the OH, which I have highlighted in blue, is bonded. The carbon with the OH is bonded to 1, 2, and 3 other carbon. We have a tertiary alcohol. Tertiary alcohol means the carbon with the OH is bonded to 3 other carbon, and therefore no hydrogen there on the carbon with the OH, therefore cannot be oxidized further. If you cannot be oxidized further, you will not turn the color of this purple KMnO4 acidified into colorless because it cannot be oxidized further. So I don't need to look at A anymore. The next one is a 3-methyl butane 2-ol. So it's a 3-methyl, so it's a CH3 at position 3, and it's a butane 2-ol, so it's an OH at position 2. First of all, what do we have? We have a carbon with the OH is bonded to 2 other carbon. There's a hydrogen there. This is a secondary alcohol. So you can be oxidized. Yes, you can be oxidized. It has a CH3CHOH. So this is your CH3CHOH. So meaning to say it will give you the positive iodoform test, which will give you the yellow precipitate of triiodomethane, or what you call iodoform. The CH3, C, and then there's a HOH. I've already gotten my answer, which will be B. Let me just very quickly show you why C and D cannot be the answer. So pentane 1 all, so there is just 1, 2, 3, 4, 5. Yes, it's a primary alcohol. Primary alcohol, you can oxidize it, but no CH3CHOH, so no iodo form. Therefore, C cannot be the answer. How about D? D is pentane 3 all, so you should be able to sketch the skeletal formula very easily. The same thing, there's no CH3CHOH. This is a CH3CH2, CH3CH2, so C and D cannot be the answer there, and the answer must be B. Moving on to the next question, question 27. So you want to test proof is a ketone. Proof is a ketone. So which pair of test result will prove? So meaning to say you need both of the tests. Let's see in A, tolerance reagent is negative, so it is not aldehyde. Well, which can be true for ketone, because tolerance does not oxidize any other thing apart from aldehyde. And then X reacts with alkaline aqueous iodine. So if I say alkaline aqueous iodine, OH minus, aqueous I2, it give me a plus. So the minus there means no reaction. Here mean I have a yellow precipitate, which is the triiodomethane, so or something called iodoform, CHI3. So this is a test for CH3CO or CH3CHOH, just as we have done just for question 26 just now, and therefore it can prove that you have a ketone as well as alkaline aqueous iodine, but it could also be distinct, so it does not 100% prove that it's a ketone. This is a test for aldehyde, it's not a test for ketone. Alright, so that's how I can tell that A is not a very convincing answer. I should really move on and check the other options. So it said X can be reduced by lithium aluminium hydride. Lithium aluminium hydride is a common reducing agent. It's a source of H minus. If you think about it, Li plus, AlH4 minus. There's your aluminium, H in a tetrahedral environment, 109 degree. Don't forget the negative charges on the aluminium when you form 4 covalent bonds, tetrahedral geometry. Your source of H minus is your reducing agent that can attack any carbonyl, or in fact carboxylic acid as well. So carboxylic acid can be reduced, ketone can be reduced, aldehyde can be reduced as well, etc. In A2 you will learn that there are other functional groups that can be reduced with LiLH4 as well. So just because you can be reduced by LiLH4 does not mean you are a ketone. So not a very convincing one at all, because the question did say proof, so both of them must react with ketone. Okay, so X reacts with 2,4-D and pH. 2,4-D and pH will give you orange crystals or orange precipitate with only ketone and also aldehydes and or ketones. So there's a classic test for aldehyde and ketones, but together they say no reaction with phalanx. So no reaction with phalanx means cannot be aldehyde. Therefore together these tests and these tests will confirm that it must be a ketone, because it cannot be aldehyde. Therefore it must be ketone if it cannot be aldehyde. Let me just show you why D is wrong very quickly. They say X reacts with HCN. Don't forget that if you have aldehyde like this, you can add HCN onto the carbonyl and you can get RO OH like this. But it can also work if you have ketone, where you could add HCN onto the carbonyl as well, mechanism of which you can find in my not topical playlist anymore, but what do I have now is the A-level concept tutorial videos, where one of the 5 key organic mechanisms covered in A-level chemistry, one of which is this nucleophilic addition mechanism, has been explained in detail, and those videos were never deleted in the first place. So both of them react with HCN, and both of them can be reduced with lithium aluminum hydride. This one will give you primary alcohol. So if I get that, then I get primary alcohol, and if I reduce that, then I get secondary alcohol. Okay. Moving on to the next one, question 28. So what I have is carbon, and I have NaBH4, which is also a reducing agent. Not as strong as lithium aluminum hydride in the previous question, but again, it looks exactly the same. Na plus BH4 minus. So what we have is this tetrahedral, 109 degree with a negative charge on the boron, with 4 bond pair and 0 lone pair. So a lot of these come down to revision of your shape of molecules, where the 4 bond pair repel equally, and when you sum up the bond pair and the lone pair, you get what you call the electron pair, and you get 4 plus 0, which is 4. That gives you boron sp3 hybridization, because 1 plus 3 gives you 4 electron pairs altogether. And hybridization is a key thing in AS concept, which you can find out under the A-level concept videos, where I talk more on hybridization. This question is on organic chemistry, so I will not talk too much about hybridization anymore. Let me just copy that correctly. So what we have here is we have a couple of regions here. This is alkene, and this is carbonyl. The other one is a carbonyl because there's delta minus and delta plus. This is an alkene. This is an alkene. Whereas the other one is a ketone actually. Ketone. So what do we have here? So if we reduce this thing with NaBH4, don't forget what I just said about hydride. Hydride means you have H minus like this. This is a rich source of electron. Alkene contain the pi bond, so you got the carbon-carbon pi electrons. Carbon-carbon pi electron is rich in electron. This is rich in electron because it's a nucleophile in this case. So it will attack this electrophilic carbon, but it will never ever attack alkene. So you never ever can reduce alkene using NaBH4. You can only reduce alkenes using the hydrogen, molecular hydrogen and nickel catalyst as your classic reduction. You name it hydrogenation, but it's actually reduction reaction. So what we say is the alkene will never be reduced by a hydride reagent, but the alcohol can be reduced by a hydride. Sorry, the ketone or the aldehyde can be reduced by the hydride to give you the respective alcohol. And looking at the options given, there must be option A. The rest of the options are incorrect. Question 29. So you're looking for two things. You're looking for chiral and reacts with Na2CO3, so there's your sodium carbonate to give CO2. So this thing here tells you it's a carboxylic acid because these are organic acids, so they have H plus chiral. So you're looking for 4 groups that are the same. If I just 4 groups that are different on the same carbon. I don't know what's wrong with me today. Anyway, I'm just going to convert it to skeletal formula. It's important that you can draw skeletal formula for whatever they throw at you. This is not a chiral center because all of these are sp2 carbon. So all are carbon sp2, no chiral carbon. So yes, you have carboxylic acid, but no chiral carbon. Your options become limited now. Okay, so I can move on. So what do I have next? I have OH and the thing with here, which is CH3. In the proper skeletal formula, I don't draw the CH3. So in a cyclic structure like this, you can imagine viewing this half thing there. So this is CH2, CH2, CH2. This cannot be chiral. This is a carbon sp2 that cannot be chiral. You have a chiral center there. Yes, you have chiral center, but this thing is alcohol. Alcohol is not acidic because it is not a carboxylic acid. Alright, so B cannot be the answer. If I look at C, what I have is I have an ester. Not too sure if you can see it, but I'm just going to draw skeletal out for you. Hopefully you can read it. HCO2 CH, there's a H, CH2Br, and there's a CH3 there. So make sure you can read skeletal formula properly. Now this is an ester. An ester is not acidic. In fact, an ester is formed from a carboxylic acid condensing with an alcohol. So So even though you have a chiral center, but you don't have an acidic carbon, therefore, if A, B, and C cannot be the answer, then D must be the correct answer. And let me just show you using a skeletal formula what it means. So CH3, CH2, CHBr, and then CO2H. So if you can see CH3, CH2, CHBr, CO2H, then we have a chiral carbon there. We also have an acidic group there. So that's why, you know, option D is the very straightforward answer there. Question 30 should be able to do it on this page. Let me go through the skeletal formula because there's nothing I like better than skeletal formula. It's beautiful, it's elegant, it's what a complete chemist should be able to do. All right, so this is X. What is the molecular formula of X? Well, let's play around and count our carbon. Let me use a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 carbon, which means, you know, option C and D are definitely wrong already. Option C, option D, you can cross them out because they do not have 10 carbon. I've just, you know, shown the carbon. That's the easiest thing to count. Now for A and B, it's just the hydrogen that's different. So I'll now count the hydrogen. In fact, what I'll do is I'll put down the hydrogen perhaps. Carbon form 4 bond. This is a double bond being shown to carbon. So there must be 2 hydrogen. So there's 2 hydrogen there. Carbon form 4 bond. So 1, 2, 3 already shown. So there is not 3 hydrogen. There should just be 1 hydrogen which are not shown. There's 1 hydrogen there. There's 0 hydrogen because carbon form 4 bond. Carbon from 4 bond, there's only 1 bond being shown, so there's 3 hydrogen. Carbon from 4 bond, so there's 2 hydrogen because you only show 2 bond. This is a carbon from 4 bond, so you still have 2 more hydrogen. Carbon from 4 bond, carbon from 4 bond, so you know you have 3 hydrogen there. Carbon from 4 bond, you have 0 hydrogen there. Carbon from 4 bond, so 1, 2, 3, so there is 1 hydrogen there. Now let's count our hydrogen. So if I use a different color, let's say 2, 3, 4. 4 plus 0 is 4. 4 plus 3 is 7. 7 plus 3 is 10. 10 plus 0 is 10. 10 plus 3 is 13. 13 plus 1 is 14. And then, have I miscounted? I might have miscounted. Have I miscounted anything at all? Okay, let's start counting again. I think I lost count of my okay, let's start. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 18 hydrogen altogether, and I have 1 oxygen courtesy of the alcohol. This means only option A and not option B is the correct answer. We have now reached onto the last 10 questions of this kind of MCQ. So the best way to do these last 10 kind of MCQ, the strategy is to check number 2 first. So in this question 31, if I check number 2, they said decomposition of N2O. So N2O gas decompose to give me N2 gas plus O2 gas. Let me try and complete the equation, or at least balance the equation, not complete the equation. So 2 of it will give me 2N2 and 1 O2 gas, like that. So what can I say there? Okay, so I can work out the enthalpy of reaction. So the enthalpy of reaction here, sorry, this is statement 2. Enthalpy of reaction given the enthalpy of formation. So I can use my formula straight away. So it's the sum of formation of product minus the formation of the reactants. A lot of students, when they do these kind of questions, they forget to label that is the formation. We must always remember it's the formation of product minus the formation of reactants, and not just product minus reactant, because that doesn't make any sense. So the formation of nitrogen is 0. The formation of oxygen is 0 because these are elements. I should have mentioned that earlier. So we are just getting, you know, nothing at all. It's just 0. They don't give you that at all. So what we have is just 0 minus 2 times that for N2O, which is plus 82. Without doing any calculation, you have 0 minus 2 times plus 82. You can do the calculations. I can tell you it'll be negative, meaning to say it's exothermic. Therefore, option 2 is correct. Moving on to option 1. If N2O is oxidized by O2, so meaning N2O plus O2, giving you NO2. Let's balance the equation. So 2 nitrogen there, because N2, there are 4 oxygen, minus 1 oxygen, I need 3 oxygen atoms. That means I just need to balance this with 3 over 2, because 3 over 2 times 2 give me 3 oxygen atoms. Now, I'm going to find this enthalpy of reaction using the exact same formula, the formation of product minus the formation of reactant. Of course, I don't need to, I don't need to write down the formula all the time, but I'm just, rewriting it so that you probably have it reinforced in your brain a little bit better. So the formation of the product here is 2 times the formation of NO2, so 2 times plus 33, minus bracket 1 time plus 82. This is for the N2O. Again, this is an element, so it's just 0 for the oxygen. You could do that on your calculator and you will get 66, well, plus 66 minus plus 82, you will get minus 16 kilojoule per mole. Alright, so they say 16 kilojoule is released per mole of N2O. So this equation was written for per mole of N2O. What is going to be my enthalpy change is energy release, because it's exothermic, so it's energy release. And based on your balance equation is per mole of N2O, so this statement is entirely correct as well. Leaving me, I have to check option 3, the reaction between NO and oxygen. So NO plus O2 giving me NO2. Balancing this equation, I have 2 oxygen atom minus 1, I need 1 oxygen atom, so I have half there. So I could very quickly do my formation of product, so 1 time plus 33 minus the sum of the formation of reactant. There's only NO that has the formation data, because O2 is an element, so the enthalpy of formation is again 0. So plus 33 minus 90, well, plus 90, this will give me negative value. I don't need to calculate it, because this is plus 33, this is minus 90. So again, it's negative, it's lesser than 0, it's exothermic, so option 3 is correct. So 1, 2, and 3 are all correct. So therefore, option A is the answer there. Question 32, which statements are correct? So if I check option 2 first, if I say enthalpy of formation of hydrogen, well, enthalpy of formation of hydrogen is going to be 0, because H2 is element. Alright, so enthalpy of formation of the element is going to be 0 because of the definition. And because number 2 is wrong, so number 2 is wrong, I really do not need to check any other answer. Only D is the correct answer, because if 2 is wrong, by logic there can only be one answer based on the options given. Question 33, so they say Kc has a unit of mole minus 1 dm cube. So Kc unit of mole minus 1 dm cube. They say which of the following could be the equation. So let's check number 2 first. So P plus Q giving you R, all of these are aqueous. So my Kc will be concentration of R over concentration of P, Q. The power is all to the power of 1 because of 1, 1, and 1 in the stoichiometric equation. So there is mole per dm cube over mole per dm cube times mole per dm cube. Hopefully you can see that the mole per dm cube cancel one of that, and I don't care about this thing because we don't have the actual value. Let's just have a look at the unit. So 1 over this thing will give you mole minus 1, and then 1 over dm minus 3 will give you dm cube. So this is correct. Option 2 is correct. Now let's go back to option 1. Option 1 have A plus B giving me C plus D. So this is aqueous, solid, aqueous, and aqueous. So Kc again is D to the power of 1. Well, the concentration of D to the power of 1 divided by both of these concentration, both to the power of 1. And hopefully you can see that because this expression looks exactly the same as these, they are just different reactants. But what you will have is you will have exactly the same unit expression without me having to do it. You can hopefully see that mole per dm cube over mole per dm cube square will give you mole minus 1 dm cube. So option 1 is also correct. Going straight to option 3. In option 3, you have W plus 2x, so something that looks a bit more complicated. This is aqueous, and aqueous. So what we have there is Kc y to the power 1, z to the power 1 based on that. And then we have W to the power 1 and x square. So what can I say here? The unit is going to be mole per dm cube times mole per dm cube. So there's mole per dm cube square. Doesn't matter, I could have done square there, but I just want to make it like this so that it's very clear to you what is going on. At the bottom there is mole per dm cube square. So now hopefully you can see that because you have two multiple of it, because you have the square due to the square there, due to the 2 in the molar stoichiometric equation. So mole per dm cube square will cancel with 2 of them, and therefore I still left with 1 over mole per dm cube. 1 over mole per dm cube will give me exactly mole minus 1 dm cube. So this is the unit I want based on the unit of Kc given the question. So 1, 2, and 3 are correct. 1, 2, and 3 are all correct. So this must be option A as the correct answer. Question 34. So what do we have in question 34? We have an equilibrium equation. So CO gas plus 2H2 gas giving you CH3OH gas. This is a very famous reaction. Actually, it's called the Sn reaction, SYN reaction. So that's the specific name of this reaction because it's synthetic methanol produced by reacting carbon monoxide with H2. It's a classic example of a reaction equilibrium. So what are they saying? They're saying that this thing was carried out at 4 times 10 to the 3 kilopascal and also 1150 Kelvin. Don't forget that Kelvin converted to degrees Celsius, you just need to take away 273 because from degrees Celsius to Kelvin you add 273. Going the other way, you just subtract 273 from 1150 to get to degrees Celsius. Anyway, this looks like a question on Lee Chatelier Principle. Lee Chatelier Principle is stated in the syllabus as something that candidates should be able to explain, state, as well as use in explaining all this equilibrium stuff. Let's check option 2 first. They said that lower temperature means decreased temperature, rate decreases, which is true. But then they say because, this is the reason they say forward reaction is exothermic. They're trying to trick students who don't know this difference. Rate versus thermodynamics, meaning to say all that equilibrium stuff in the context of reversible reaction, reversible changes under equilibrium. Rate versus thermodynamic is a very, very common confusion among a lot of students. This is a statement, this is a correct fact, but not for explaining rate. Okay, it's used to explain equilibrium position or equilibrium yield when temperature changes. So you can't use this reason to explain rate. In order to talk about rate, we need to talk about collision frequency, and also in air level or in AS level, you got to talk about so it's not plus, it's N. You got to talk about the Maxwell-Boltzmann distribution, which is the Maxwell-Boltzmann energy distribution. So because the reason is already wrong, they talk about equilibrium position, equilibrium yield as a reason here, giving forward reaction is exothermic. It can't be used to explain rate. So 2 is wrong. If 2 is wrong, therefore D is answer. Okay, so we can't choose any other answer because 2 is wrong. So straight to the point, D is the answer there. We can move on to question 35. What do we have in question 35? Let me just do on a new page. Question 35, they say relative electrical conductivity. So all of these are to do with period 3. So I might as well just draw for all of them. This is part of your inorganic chemistry under periodicity. You just don't know which trend is going to come out. So sodium, magnesium, aluminium, they are metals, so therefore they can conduct at room temperature as solid. More importantly is they become better conductor, so greater strength of a metallic bond because more valence electrons get delocalized. So group 3 will delocalize 3 valence electrons versus 2 valence electron being delocalized versus 1 valence electron being delocalized. So therefore better conducting because you have more free electrons in the giant metallic structure. So very important, there are more free electrons in the giant metallic I don't want that. Let me see if I can move that better. More free electrons in giant metallic structure. Anyway, so silicon is a semiconductor, and then you can think about from phosphorus such as P4, S8, and then Cl2 and then argon. They are all non-conducting at all. So before I look through the options, I should really be thinking about, let's just sketch it out. Okay, let's just sketch out how our conductivity would look like. So if I have electrical conductivity, so it will go up from sodium, magnesium, aluminium, and then it will go down to silicon, which are not very conducting at all. Perhaps I should go all the way down there. Alright, so silicon, and then it will jump all the way down there to P4Cl2. What else can I say? S8, P4 and then S8 and then Cl2 and then argon. So they are non-conducting at all. So let's have a look at the options. So if I check number 2 first, so they say greatest to least, right? Greatest to least, from the best conductor to the worst conductor. So they say aluminium is better than magnesium, better than phosphorus. Aluminium is better than magnesium, better than phosphorus. Number 2 is correct. Let's check number 1. Sodium is greater than silicon, greater than chlorine. Sodium is a metal, better than the semiconductor. So semiconductor for silicon, used in silicon chip. As you know, a lot of electronic products, they have silicon chip inside because they're semiconductor. Big and huge industry inside there. Much more conducting than chlorine, which is a non-metal. So number 1 is correct. If we check number 3, sulfur is more conducting than silicon, more than phosphorus. This thing is wrong, because sulfur there is a non-conductor, whereas silicon can conduct electricity. So since that thing is wrong there, how do I put this wrong there? So therefore 3 is wrong. So if only 1 and 2 are correct, therefore we're looking at option B there. Question 36. So we have 3 test tubes X, Y, and Z. Each contain water. So we are talking about hydrolysis actually. Hydrolysis of period 3 chlorides is part of AS case study. So you gotta add a universal indicator solution which will change color, and then you can refer to the color chart as for what pH that is corresponding to. You're looking for correct statement. So let's think about the chemistry. NaCl in water, that is just going to dissolve, so there's no hydrolysis, that would just be pH 7. There's just a table salt in water really. SiCl4 in water will hydrolysis, and you will get if I just write a equation for it, so SiCl4 plus H2O, that should give you SiO2 plus HCl. You have 4Cl, so I'll get 4HCl. Now I need to balance it with 2H2O. So this is a white solid. As you know, SiO2 is insoluble in water. This one can be given out as a steamy white film. So very exothermic reactions, because it goes from simple molecular to a giant covalent structure where you have a lot of strong covalent bonds. So very exothermic reaction there. hydrolysis there produces a very strong acidic gas, so there will be pH2, pH3 like that. So what is this? This is Y, right? So this is Y, this is X. So pH in test tube X is 7, that is correct. pH in test tube Y is going to be acidic due to the HCl produced, pH2, that's correct. So here I've checked 1, 2, and 3. Okay, so let me check number 3. So this was option 1. So option 2. Now option 3 is to do with AlCO3. So AlCO3 plus H2O. The first thing that happens is they form a complex like this, where you have 6 water surrounding the Al3 plus and you get 3 Cl minus. So that is just what happened initially, where the H2O replaces the Cl to give you this particular complex. Let's not worry about the stat symbol for the time being. So what happened with Al3 plus is Al3 plus is very small size. As you know, ionic radius decreases from sodium plus to magnesium 2 plus to aluminum 3 plus. These are from the data booklet. You must be able to explain them in terms of counting number of protons, counting number of electrons, and think about the effective nuclear charge. So this thing is bigger than this, bigger than that. And this one is very high charge. So as a result of it, so the aluminium H2O6 3 plus can be further hydrolyzed, if you think about it, in the presence of another water molecule. I don't really want to think about reversible, I guess, because there's for magnesium 2 plus aqueous solution. That's why MgCl2 hydrolyzes to give only a very weakly acidic solution, because there was in equilibrium. Aluminium 3 plus will not be in equilibrium. That's why it'll give you a strong acid. So now you're left with 5 H2O, and one of them become OH minus because you dissociate into H plus. So this is OH minus, this is Al3 plus, now you have 2 plus, and you have H2O picking up the H plus that you lose, then it become like that. So what happened there is, this is not an equilibrium, so this gives you pH2, strong acid. Some book would show you as pH3, totally acceptable. So there is your statement number 3, and that is your test tube Z. So that is entirely correct. So 1, 2, and 3 are all correct. So there's option A there as your correct answer. Question 37. So this is an organic question. Well, it looks like an organic question. So let me see what I can do. So it has got a carboxylic acid. It's got a ketone. So this one there is a ketone. This one here is a carboxylic acid. So these are all functional group that you have learned. Let's check number 2 first. What is number 2? So 2 groups. They said 2 groups. Strong absorption. So this is about infrared. So 1640 to 1740 wave number. So here you have 1 times CO of a carboxylic acid, and here you have 1 times CO of a ketone. Clearly this is different from this, and that's why you get 2 absorption, and this corresponds to CO, 1 for ketone and 1 for carboxylic acid. So very clearly option 2 is entirely correct. If I look at option 1, it says MR of 116. Let's check for the molecular formula. So count the carbon, 1, 2, 3, 4, 5. So there are 5 carbon. Let's count the hydrogen. Carbon from 4 bonds. So let's play this game. Carbon from 4 bond, you only show 1, so there's 3 hydrogen there. Same thing there, 3 hydrogen. Carbon from 4 bond, so carbon from 4 bond, 1, 2, 3, so there's 1 more hydrogen there. Carbon from 4 bond, there's 0 hydrogen. Carbon from 4 bond, there's 0 hydrogen. There is 1 hydrogen there. So you're going to add 1 plus 3 give you 4, plus 1 is 5, 5 plus 3 is 8. So you have C3H8, and you have 1 oxygen, 2 oxygen, and 3 oxygen, so C5HNO3, which you can work out the MR. So 5 times 12.0 from your data booklet. So 8 times 1.0, and then 3 times 16.0. And yeah, put it into your calculator and you get 116.0. So you know this thing is correct again. How about option 3? What do I have in option 3? It says between 2500 to 3000 wave number is sharp and strong. So we know that the other significant absorption here would be this group here, the OH. So the bond OH will give us a strong broad absorption, not a sharp absorption. So the OH of the carboxylic acid is strong. Yes, strong is okay, but very, very broad. If you look in the data booklet, you get a non-broad means not sharp. So since that thing is wrong, so number 3 must be wrong. Don't know why I circled that. I should really just put a cross on it. Therefore, only 1 and 2 are correct. We are looking at option B. Question 38, so nearing the end now. So during the bromination of methane, blah blah blah, so what could be produced in the termination step during bromination of propane? So we are looking at termination. So termination is when radical recombine together, and we are looking at for propane. Propane is 3 carbon. So what we could have is, you could imagine we could have 3 carbon like this. Let's see, this versus, well, not really versus, or you could have this, because the radical could be at the end there, or it could be in the middle, but it could be there and it will be the exact same thing because, you know, symmetrical about the center. So you have these and these. If you imagine that if you have these and these combined, so let's have a look at option 2 first. Option 2 shows you CH3, CH, CH3, CH, CH3 twice. So let's try and convert this to skeletal formula. As you know, I'm a big fan of skeletal formula, so we gotta always try and draw skeletal formula. Looks a bit scary. CH3, CH, because carbon from 4 bonds, so CH3, CH, CH3. CH, CH3 twice. So, you know, how do we get this thing? You can hopefully see if we chop off here or if we fragment there. So it's that thing plus that thing. So it comes from this radical here, which can come from propane as part of the termination or the 2 radicals recombined. So this option 2 is entirely possible. How about option 1? If you look at option 1, CH3, CH2, CH, CH3, CH2, CH3. So let's try and convert that. CH3, CH2, CH, CH3, CH2, CH3. So how in the world do I get that? Well, I could chop there. Then I will get like this. But this is 4 carbon and 2 carbon. Impossible from impossible. Did I spell possible correctly? Impossible from propane, which is 3 carbon. Then how about if we chop off at different places? If I chop off there, that's even worse. Then I will get like this and like this is 5 carbon and 1 carbon. Again, it's impossible. So, and you can think about different scenario where you can chop off there. That will give you 2 carbon and 4 carbon, which is this scenario. 4 carbon and 2 carbon, which is the first scenario. So that's how I know I shouldn't circle it. That's how I know 1 is impossible, because there's no way you can get the fragmentation that come from 3 carbon and 3 carbon that you get from propane free radical substitution reaction. So number 2 is correct. Number 1 is definitely incorrect. So therefore, there can only be one answer. So the answer must be 2 and 3, because 2 is correct, 1 is wrong. So answer must be C, which is 2 and 3. Now let's have a look at why number 3 is correct. So we already gotten the answer, but it's important to understand why the answer is the answer. I mean, there's the specialty that I'm trying to offer on my channel, which is trying to think out loud, because we are expected to be able to explain anytime, any day. So CH3, CH2, CH2, CH, CH3, CH3. how can we fragment this? I can imagine this being like this, and I can fragment it from the terminal radical, the radical is at the end, or I can get it from the branch radical combining with these. Then I can see that my radical is there and my radical is there, and both of these you could get from 3 carbon propane. Both of it you could get it from these as well as these. When these and these combine together, it's entirely possible for you to get this particular thing. So 3 is obviously correct, and we already knew that was the answer because we checked 2, which was correct, and we checked 1, which was impossible. So 1 was impossible to get from 3 carbon and 3 carbon, and therefore this left us with 2 and 3 without even checking for 3. But that was what I did anyway, just to convince myself and to convince you that 3 is definitely correct. Question 39. 3 reactions of primary alcohol. So primary alcohol, first of all, reaction with corn HBr. So if I check option number 2, that was what I meant when I circled that 2. So when I have, let me just exemplify with a primary alcohol. The carbon with the OH is bonded to one other carbon. So when I react it with HBr, in fact this is concentrated HBr, I can get Br like this, and I can get H2O. So this is a classic nucleophilic substitution to get the halogen alkane from the alcohol. So 2 is entirely possible. And of course, your primary alcohol can react with ethanoic acid. Ethanoic acid, 2 carbon carboxylic acid. You're going to remove the OH from the acid and H from the alcohol, and you will get an ester. So I'm drawing my ester from the other way around. Usually the ester is drawn from this way around, but you will hopefully see that it really does not matter whether you draw it this way or this way. You're going to get the exact same product. This is called ester, and of course you will get H2O as well. They are the same product, so you just get one ester. This is named ethyl, ethanoate, because you name the alcohol bit first. The alcohol bit is the one without the carbonyl. 2 carbon ethyl, 2 carbon carboxylic acid will give you the 2 carbon ethanoate. This reaction is called condensation. It's a type of reaction stated in the AS syllabus. Let's check option 3, passing the alcohol vapor over heated Al2O3. So this is heat, and this is actually used as a catalyst. So this is a condition for elimination of H2O. So you will kick out H2O by passing alcohol, simple alcohols, over the catalyst Al2O3. And yeah, I mean, you get alkene, and you get this alcohol forming alkene. This is actually elimination. The type of reaction is elimination of water. Sometimes they also call this as dehydration because you are removing H2O. So 3 is entirely possible. 1, 2, and 3 are all correct. So they give you option A for that question there. On to the last question of this paper 1 tutorial. So it's gotten long enough. I'm getting tired already. But anyway, let's just finish this one off. So what do we have? Our polymer. Hopefully I don't have to draw the whole thing, and hopefully it will make sense to you. I'm not going to draw the whole thing actually. CO2CH3. So you can see there's the repeating unit. And obviously if you can't see this, then you know it's probably worth it if I draw out the monomer. So this is part of the polymer repeat unit. If I draw out the monomer, I'm working backwards, so I get back my carbon-carbon double bond, and I lost the extended chain. Then what I'll get is I'll get a CH3 and a H. I wouldn't draw a fully display format, but what I'll draw is I'll show the ester, so that is very, very clear that there is the ester bond, and this is the ester bond that you have formed. This is the alcohol bit, and there is the carboxylic acid bit, well, carboxylic acid component. Probably should move that monomer somewhere down there so that it's not confusing. Alright, anyway, so let's have a look at option 2. Option 2 says NaOH. So NaOH aqueous and reflux. This will hydrolyze ester. This is hydrolyze the ester. This is base hydrolysis of ester. So number 2 will definitely react. Alright, how about sulfuric acid? Well, that will be acidic hydrolysis of ester. Of course, you also need a reflux. You can also hydrolyze the ester. This is called ester acid hydrolysis. This is base hydrolysis of ester. This is acid hydrolysis of ester. Of course, when you do base hydrolysis of ester, then you will get a carboxylate salt, which is a sodium salt. See, when you use sodium hydroxide rather than a carboxylic acid, but the alcohol will be whatever you expect it to be. As for the acid hydrolysis, you get the carboxylic acid, which will be present as the acid form, and the alcohol remain as just the alcohol, because normal alcohol is not acidic, it's not basic at all. Number 3 is sodium. Sodium reacts with OH group, whether you have carboxylic acid or whether you have alcohol group. But the thing is, in the polymer, we do not have any hydroxyl OH. We have an ester. This can be hydrolyzed to give you alcohol or carboxylic acid or the salt of carboxylic acid. But within the polymer itself, within the polymer which come from the monomer, these are the polymer, all right? So not the monomer actually that will react, but it's the polymer that reacts, because these reactions, they have specified with the polymer, X. Should really write that properly, with the polymer X. So within this particular polymer, there's no OH hydroxyl at all. So this thing will have no reaction whatsoever. 3 is wrong. So only 1 and 2 are correct. So there's option B as the only correct answer there. Alright, I've come to the end of these tutorials. This is a restructured format of my paper 1 for the Cambridge International 9701. Hopefully that have been useful. Not too sure. I've tried to retain my old style of chattering through the tutorials, covering a bit more concepts than whatever is needed. Some people found those kind of things useful as they recap some ideas as I go through the questions. Some people find that completely useless. Different people have different opinions, and I totally respect that. Alright, if you have found my tutorial useful, so do support the work. Click the button on the bottom right. Do share the channel widely with all your friends who might have thought the channel is dead, but the channel is not dead. I will still keep on going, and there will be more tutorials coming out in the future in this kind of restructured format, where you can find your own question paper. I'm just going through the questions so that I won't be breaching any copyright issues. Thank you for watching. Follow me at ptet.chemistry. That is ptet.chemistry on Facebook, Instagram, and Twitter. And again, click the button on the bottom right to subscribe to the channel and share the channel widely with everyone you know. Thank you for watching.